Hi guys, welcome to this video on the normal distribution. Now, I apologise if it sounds a bit echoey today. I'm just having my kitchen done and there's nothing in here apart from myself and a table, so it's pretty echoey. Now, before we get going, we really do need to understand the difference between discrete variables and continuous. And that is something we've spoken about a lot at this point, and we've done a lot on discrete variables in the binomial distribution, for example. And now we're going to actually move on to something that's continuous. So what do you mean? So discrete is data that can only be written as exact values. For example, height of someone. No, that's a really bad example. That's continuous. Shoe size, like a size 7 shoe. Well, actually, people could be a size 7, but their feet would actually be different lengths, but it would just fit in that category of size 7. Things like number of sixes rolled or number of goals scored. You can't score 1.2 goals in a game. Now, continuous, there's actually an infinite amount of values that data can take. So heights of people. I'm 172 centimeters. Actually, I'm not. I'm 172.4. And that 0.4 means a lot to me, as that's quite little. Right. So that's out of the way. So let's have a look at it visually. So the one on the left is a discrete. You can see those bars because they can only take certain values. There is nothing, for example, in between this 5 and 6. The bar you can see is going either side just because it's easier to see than a line, but in theory they should just be lines. And on the right here, we've got the average height of a flipped coin, and that is continuous. And this shape, this curve shape, we've spoke about before. When we were talking about skewness, and this one is negatively skewed. It's stretched towards this end here, and that's what a continuous variable is, because between 15 and 20, there's an infinite amount of results that it could be. Now, this is what we're looking at today, the continuous distributions. And it's really important to understand this fact here, that the area under a continuous probability distribution is equal to 1. Now, the normal distribution, you won't have that skewness, it will be perfectly symmetrical. So I've got a few examples here. Now, if we look at the random variable being height of men, this is obviously continuous. And if we draw that, it would look something, bear with me a second, something like that. This is designed to be symmetrical and a nice smooth curve. My stylus isn't the best, so that's what we've got. Now, I've tried to make this line up with the top of this bell-shaped curve. And this is where, if it's symmetrical like this, it would be centered around the mean. We use that symbol mu for the mean. In fact, it's the mean, the mode, and the median would all be on that line. It's when the data is skewed, it's when the median is stretched from the mean. But that's another video. Okay, so let's say this is 172. Let's feed my ego. Let's imagine that is the average height of a man. It's not. And what these little marks here are the standard deviations above and below the mean. And this is important because let's imagine, if you're watching this video, probably in the sixth form, whether you're male or female, I know I've said men here, but male or female, you have to buy clothes to wear to work, possibly a suit. Now, this information here would be really important to a clothing company because they want to know what sizes to make. They're going to make loads of sizes, loads of outfits for people in here. They're not going to make many for these extremes because they go out of business. So the standard deviation above and below the mean is really important. And you'll notice I've only got three marks. We don't normally go past. There are more, but you can see here the gap between the lines. It shouldn't ever touch a line. It should just tend towards it. and that's to represent all of the data, because remember, the area under this curve is 1, probability of 1 is everything. Let's have a look at some of the other shapes, and we'll talk a little bit more about this standard deviation. So I'm making this video with a nice bottle of wine, so I just thought, well, let's make this example about wine. Now, these companies, it's a manufacturing process, and even though the mean is 75 oh, let's just change that to centiliters. I could have written 750, but I didn't. Should have. That is the mean, so we'd expect every bottle to be really close to that. These companies, they test for it, but sometimes it'd be less, sometimes it'd be slightly more. But what would happen, because most of the results would be really close to the mean, you'd end up with something. So I tried my best. Imagine that's symmetrical. But these results would be much closer to the mean than, for example, the height of everyone. There's far more variety of people. The bottles of wine is a controlled test. It'd be much closer. It could be a lot higher as well. Mr. Beard has been training for the marathon. COVID-19 has cancelled his dreams. Sorry, Mr. Beard. But if we look to run a marathon, well, I say 4 hours is probably, I don't think that's an average. I think that's a good time, 4 hours. I've never done it. But you probably find if you did a normal distribution for the times of a marathon, it would be a lot lower. So it might be something like this, because the majority of people will be a bit further away from the average. So if this is time, this is your elite runners, and these are probably the people wearing those big fancy dress costumes, and this is where most people would be. Now, so when I was talking earlier about the suits, what we need to know is in between plus and minus 1 standard deviation, there is actually, I'm just going to change, that's horrible, 68% of the data. So these companies, if they work out the mean, if they find everyone's height, or a big sample of everyone's height, and they work out the standard deviation, plus or minus 1, they get 68% of the population. So that's where they can make most of their sizes. And you probably find for a male length of trouser, that's like 32 inches, for example. 30 to 32. Now, let's do it on this one. If you go to 2 standard deviations, that actually accounts for 95% of the population. And if you go to 3, which on mine is actually everything, it's not 100%, but it's 99.8%. So that's why we don't really go past 3 standard deviations, because it doesn't really tell us much. So how do we write these distributions? Like for example, for binomial, you're used to writing it in a certain form. So let's go back to this height. So we say x is distributed normally, and you're going to be told that it's a normal distribution. And then we have our parameters, but this time what we have is the mean, so mu, and the variance, which is standard deviation squared. So sometimes they'll give it to you in this form, which is really useful, but they'll catch you out when they actually give you what the variance is, and you're going to have to square root it. But we always write the standard deviation squared. So these are the parameters that you need to know. So this is just out of your textbook. I've spoken about that, population mean, population variance. We said they're symmetrical. We said it's a bell-shaped. Asymptotes at each end, like I did tell you that it does tend towards that axis. And I told you that one. And this is something that's just worth remembering. They don't often ask you it, but the point of inflection happens at mean plus or minus 1 standard deviation. We may look at that a bit later, but you'll see it in questions, and you just have to go to 1 standard deviation above. I've just done that. I'm going to talk about that again. Now, here's a question. So we've got the diameters of a rivet produced by a particular machine, X, is modelled by. So we should really specify what the random variable is. So let X be R dot B dot diameters of rivets. Okay. So X is distributed normally with a population mean of 8 and a standard deviation of 0.2 squared. That's the variance. Okay, so what we're going to have to do is always, never ever skip this, is draw a picture. This is going to be X, and I'm going to do my best attempt at a bell-shaped curve. That's pretty good. I'm going to pop in the mean, which is 8. I'm going to try and put on 3 marks, and I really want them to come towards the end. Don't put your third one in here, because it's meant to represent 99.8% of the data. And to answer both of these questions, what I'm going to do is just, I don't want all of that. Can I just wanted to copy that, I just have to draw it. So for A, probability is greater than 8. So actually what we're looking for is all of that there. So that is half. The area under the whole curve is 1. So the probability that X is greater than 8 is equal to 0.5. And I will, while we're here, is talk about these symbols. Because if they did this, that is the same answer. And with these, with a normal distribution, we actually ignore these signs really and just treat it as the same because the argument of bounds. So if we were talking, let's just get that minute, for greater than 8, so we could go to 8.00000001, for example. If you type in loads of zeros, okay, yes, it's smaller. Sorry, it's a little bit bigger, but not by much. It's more so at the other end. So if it was 7.9 recurring, your calculators, and you should understand this from bounds, will round up to 8. So the fact that it's continuous, it can get so close to the value you want, but the bounds will mean it rounds up. So actually, we're always going to treat them like this. Okay, let's try do part B. I'll draw another one of these curves. Oh, that's way worse than the first one, but it will do. So that's 8. 1, 2, 3, 1, 2, 3. Okay. Now, for this one, you can see it's 7.8 to 8.2. So I'm going to start to put my standard deviations on. Now, each of these marks represents one standard deviation. So, and that standard deviation is 0.2. So that's 8.2. That's 8.4. This one is 8.6. So they're saying, what is the probability of it being this diameter of a rivet being between 7.8 and 8.2? Well, that is there. So if you remember what I just told you, let me write this on. It's 0.68. 68% of the data falls between there. If they had changed this to 7.6 and 8.4, then we'd be looking at plus or minus 2 standard deviations, and that'd be 95%, so 0.95. I think that's pretty much it, yes. Okay. So the next video, what we're going to do is look at values that don't fall in line with these standard deviations, but it's important to practice this first, get it in your head, get confident, and then come and join me in the next video.